Okay. Okay, so here we are again. Let me perfect. Sorry. Okay, yeah. Okay, so let me get back to where we were last time. So I was talking about this point of view based on formal languages, where you can look at constructions of certain type of strings of in a given alphabet, which you can think of as strings of words in a language. And you can use this formal machinery to produce different kind of formal languages to study different kind of recursions that are possible in different classes of formal languages. So, as I mentioned, that's the way it works. You have certain production rules that tell you how you form strings in a given alphabet in a language, and you read the results of such a production, application of various production rules, and give you certain strings that belong to the language computed by the grammar that you're looking at, and different kinds. Well, I will talk about today, much more in detail about what this different classification, how this classification works. But different types of formal languages have the property that they can give rise to different types of recursions. And the example that I was talking about last time is where we finished the class last time, is that, for example, in the most restrictive class of formal languages, which is the type 3, the regular languages, which are the ones that correspond to the finite state automata. For example, you can produce things that have loops, but they kind of have independent loops where you cannot control the number of times that you go around one of the loop and the other one simultaneously. They're kind of independent variables. But if you want, for example, a kind of language that produces a recursion where you're fixed the number of times that you go around in different loops, then you need a context-free rather than a regular grammar, because you need some kind of, so the regular ones are memoryless, the kind of Markov processes on a graph, paths on a graph. But the number 2 requires storing in memory the number of times that you're going around the loop, so require an infinite amount of memory storage. And as I said, there was this conjecture very early on in the study of generative linguistics that the context-free grammars would be enough to account for the natural languages. And as I said, that conjecture turned out not to be true. And so how one proves that it is not true is by exhibiting an example of a recursion that exists in some natural language and that cannot be produced by a context-free grammar. And so the example. So there's other examples of recursions that can be produced by context-sensitive grammar rather than a context-free grammar. So you have to kind of find something that has the kind of property that can be realized by a context-sensitive but not a context-free grammar. So the first examples that come out of that people noticed were that actually are of this kind have been noticed first in Dutch and then in Swiss German, which is actually very similar to Dutch. And they have more or less exactly the same structure. They're called cross-serial dependencies. So what that means is a dependence that looks like this. You have two loops that you can form, but they cross each other. So the idea is something like this. I mentioned even in English, you know that you can form certain kind of recursion in languages. An example is you can help someone, help someone, help someone. Right? That's clearly something that is a recursion. And you can ask someone to ask someone to ask someone. Right? That's another recursion. But in English, if I try to combine these two recursions together, I would ask someone to ask someone to ask someone to help someone to help someone to help someone. So there would not be a cross serial dependence. There would exactly be the kind of 0 to the n, 1 to the n dependence that I showed. So it is context free, but it's not. But if you try to form the same sentence in Dutch or in Swiss German, then these two recursions would have to cross each other. So the way that you do it, like this is the example in Swiss German, you said that we would have liked to ask Hans to help, to ask the children to help Hans to paint the house. So there's exactly this: ask someone to ask someone to ask someone, and help someone to help someone to help someone. But if you want to have a well-formed sentence like that in either Dutch or Swiss German, these two will have to cross. If they don't, that would not be considered grammatically correct, syntactically correct. So that's of course examples like this exist in other forms, but this is the first one that was observed. Yes.
An example where you combine to ask someone to help someone, why is that like the 0 and 1 in case instead of 0 like 1 and like why is
Well, I'm saying if you try to do it in English, right? If you try to combine these two loops, right, in English, you would have to say you would ask someone to ask someone to ask someone, whatever, how many times you want to help someone to help someone to help someone.
Okay.
So this could either be the 0 to the n, 1 to the m, in the sense that you're formally an independent source. So that would be a regular grammar. Or you could also try to force them to be the same length, and that would be realizable by context free. But you would not have the possibility of doing it grammatically in this cross serial form. So it would not require a context sensitive grammar to realize. But in this case, it would not be possible to do it with a context free case, with a context free grammar. Okay, so the result of this observation is that, well, the context free class is too small to capture all the phenomena that are known to occur in languages. For example, the kind of recursions that can happen. And the context sensitive class is clearly way too large, because there's an enormous number of things that are context sensitive and that have phenomena that are not known to occur in any human language. So at that time, the question for a while focused on whether one could identify a class of formal languages that is sufficiently larger than the context-free ones, so that they would contain the type of recursion that are known to occur that are not context-free, but would not be as large as the context-sensitive. So there have been various type of such formal languages, classes that people are focused on, and I will say a little bit more about those. Yeah.
Is there a notion of homophily in languages?
You mean, well, there are certain kind of equivalences, right? In the sense that you can describe the same language. So in a sense, the grammars, the generative grammars, in the sense of formal languages, are a bit like presentations of groups. Okay? In fact, I will talk about the fact that they are actually very similar to presentation of groups. You can kind of represent a lot of classes of formal language by presentations of groups. But so this means that, in fact, this is a good observation, because if you think of them as something like presentation of groups, the point is that you can realize the same language by different grammars. And so one of the problems that were known for the case of groups is that it's a very difficult question to say when two presentations are equivalent or not. And so there is a similar problem that one encounters here. And so there are like a certain kind of standard form that you can put the grammar in that simplify the form of this presentation of the formal language. but it still leaves you with this general problem of equivalence between them. And in fact, this is one of the aspects for which, this, over time, considered to be maybe, it's one of the difficulties with working with this formal languages approach. And okay, as I said, of course, even if one restricts to certain very specific classes, like the multiple context-free grammar, pre-adjoining grammar, but already in the context-free sense, all these problems are there. So in terms of when two presentations are equivalent and so on. So and moreover, there is another issue clearly, which is that there are lots and lots of formal languages that have nothing to do with human languages and don't have properties that are similar to the ones that we see in human languages. Maybe okay, they have similar recursions, but otherwise they clearly do not represent aspects of human language. And in particular, okay, for example, a lot of programming languages can be treated as formal languages, but also you can get. I'll talk about this more in a moment, but for example, you can get formal languages from an arbitrary finitely presented group, like if you have a discrete group with a certain presentation in terms of generators and relations, you can look at the set of words in the generators that are the identity in the group. Okay, and that is a language. This is a family of words in that alphabet, which is given by the generators of the group. And you can ask questions about what type of formal language this is. In fact, this provides a very nice supply of examples in the theory of formal languages to check different properties of formal languages. And for example, I'll say more about this today. If you have a language that's obtained from a group in this way, then this is a regular language if and only if the group is finite. And it is a context-free language if and only if the group has a free subgroup of finite index. So it's an interesting that in this case, you can completely characterize when you are in the regular languages class or in the context-free class purely in terms of some algebraic properties of a group. And this means, for example, right, that if you take the group SL2Z, SL2Z is well known for having a free group of index 2. So this is a context-free language. So, right, I mean, this means that we're very far from anything that looks like human languages. I mean, I mean, I always make this joke when I give these talks about this stuff that, okay, you could conceivably imagine someone speaking Fortran, especially here at Caltech, but I think, even here at Caltech, you will probably not encounter someone who speaks SL2Z. So it means that, okay, maybe we are dealing with a tool that is useful for certain things, but a bit of an overkill for a lot of other things. Okay. And so, there is also, if you take seriously this question of characterizing where the region of in whatever model you have for computational or mathematical, whatever model you have for languages, you can ask this question or characterize the region of this model that is actually populated by the human languages. This is a bit what I was saying in terms of what is the class of more than context-free, less than context-sensitive that will capture the human languages. And more generally, this is in a sense one of the crucial questions in the field, and that depends exactly on trying to parameterize the human languages in terms of some suitable variables. And I'll come back to this in a moment in discussing this problem of, for example, syntactic parameters, and also some attempt to coordinatize the space of languages that have been done. So for several of these reasons, this theory of formal languages is at some point was no longer viewed as the best possible way to approach giving a generative model for syntax in human languages. And the main reasons were, well, first of all, that is completely focused on strings of words rather than on structures or syntax. And I was discussing last time, our brain is clear. I mean, one can easily see that our brain is sensitive to the structure beyond just the list of the string of words in a sentence. And so this problem in itself can somehow be partially accounted for, because you can have some type of formal languages that are based on tree structures, not just on strings. So you can sort of partly correct it. There are also graph grammars, where instead of looking at strings, you look at more complicated combinatorial objects like trees and graphs. So this to some extent be corrected, but one of the other problem is this fact that anyway these things capture an enormous number of other things that are not similar to human languages, but also that when you actually start to try to explicitly model some aspects of the actual syntax of an actual language, like the syntax of English in terms of a formal language, you have to write out a lot of these production rules. And this clearly is a little dubious that you're actually doing the best thing. So in some sense, the analogy with groups is helpful, because it's like saying that the only way that you have to think about a group is by writing explicitly a presentation in terms of generators and relations. Sometimes that is useful, but sometimes that's very cumbersome and it's not capturing what you actually want to capture. And so, especially in terms of minimality hypothesis, as I was mentioning last time, of how these things could have actually evolved in a biological system like us, the fact that every aspect requires a very long description is not satisfactory. Okay, so this is the way. So I will still give you because I think it's useful to know about this. I will still give you a more detailed account of formal languages, especially because they can be useful for modeling other things. And they're used in modeling for computational biology. They're used for computer science and a lot of other stuff. So I will tell you more about formal languages anyway today, and then I'll move on to other things. But before that, I want to give a little sketch of the following steps, and I'll also fill in a little bit of details of that before moving on to the new stuff, which is the last line of this list. So, okay, started to realize that maybe one could try to do something more precise or more tailored to human languages than this overall theory of formal languages. The first shift was towards what is called transformational grammar, which is still partly based on formal languages, but partly on transformation rules not just on production rules, but on transformation rules. And then, this further evolved into two further steps, this principal and parameter and government and binding, so more, trying to explicitly identify rules of syntax, how sentences can be modified once they're formed according to transformation rules, and how different kind of syntactic construction can be parameterized. And then minimalism, which is attempt to kind of simplify this picture as much as possible. Okay, so let me just say briefly, I'll fill in more detail later. So the idea in passing from the sort of overall formal languages approach to transformational grammars is that you have some kind of two different levels of structure, which linguists refer to as deep structure or surface structure. There's some kind of deep structure of sentences of syntax that is kind of more closely related to the semantic parsing and is less language dependent. And then there are transformations that act on this structure and that produce the various manifestation of for example, the rules that we know, how we form, I don't know, how we turn a sentence into a question, or how we turn a sentence from the active to the passive voice. So these kind of explicit rules of syntax that are language dependent and no more, less fundamental in some sense. At least this was what was believed at that point. This point of view has changed also significantly in more recent time. But and then this means that if you think of it in this term, you have like a production system and a kind of system of transformations, and these two are at this level considered as like two separate steps, and these transformations are automata that act on trees and produce other trees, so they're like transformations of structures, of tree structures. And of course, in more recent theories that I'll come back to discuss that, this point of view has further shifted, and these two things are sort of packaged into a single structure, but which is different from the ones originally in the other formal languages. So the other thing that I mentioned is government and binding and principle and parameters. So the transformational grammars is mostly a lot of things that happened during the 1970s. So I'm kind of jumping like basically one decade at a time in the so brief summary of history of the field. And this government and binding and principles and parameters is largely what happened during the 1980s. And the idea is that there's some general rules of syntax, as well, rules of generative grammar, and some kind of parameterization that distinguishes what changes. So there's like some fundamental rules, common rules, and then some parameterization that distinguishes how these are embodied in the specific individual languages, right? For example, if we think in terms of tree structures, certain languages are head initial, which means that our trees sort of look like you kind of keep appending things on one direction, or they are head final, and the trees typically look like you keep appending stuff in the other direction, right? This is an immediately visible difference when you look at the structures behind sentences. Of course, one also realizes that these are not always so clear cut. There are languages that, for example, are more morphologically rich, and so the sentence structure tends to be more flexible in those cases. In German, you could have sometimes in German sometimes looks at initial and sometimes looks at final, and this is kind of puzzling at first. It turns out that part of this mismatch of directionality is due to some other parameter this verb second parameter that German has, and some other Indo-European languages like English don't have, and that sort of blocks certain structures in a way that they look at final instead of at initial. And so this is an example where people started to notice that there are these different properties of syntax that I can try to encode in different parameters, but they're obviously not independent of each other. So if you have like one parameter that captures this head directionality property, and you have another this verb second parameter, well, these are not independent variables. And there's various examples that has been seen in other languages of how this head directionality seems to be affected by the presence of other parameters. So this is an example of how this parameter side works, and principles on the other hand are sort of like more general kind of properties, that what type of transformations preserve the same sort of deep structure, like these rephrasing transformations and so on. Where how lexical properties are incorporated in sentences, and what kind of moves, kind of transformation are local or have like long distance effects in a sentence, and how far these local effects can propagate, what are barriers to propagating local effects, and so on. And So parameters, as I said, so there's a lot of them that linguists have been trying to characterize. These are some examples. So, as I said, there's head directionality. There's things like word order have to do with word order. Some languages always will put the subject before the verb. Some will do the other way around. There's a pro-drop, right? If you in some languages you can drop the pronoun and the sentence be still meaningful. Like in Spanish, you can say llueve for it rains, but it doesn't have, or in Italian you can say piove, it's like Spanish, but in French, which is also a Romance language, it doesn't work. You say piove, but you cannot say piove. It's not grammatical. In English, it's like French. You can say it rains, you cannot say rains. And so this is a language rather has it or does not have it. It's pro-drop is more general than no subject. No subject is just you can drop the subject of verb, you can drop other pronouns. So there's a lot of things and of parameters like this that are interdependent. There's also changes that are recorded in history of how this parameter works for a given language. Also, there are strange facts. For example, if one considers word order structures in different languages, so specifically the position of subject, verb, and direct object in sentences, all of the orderings are recorded in some languages, but they are very unevenly distributed across world languages. So the number of the most common configuration is subject, object, verb. And the ones that we do use in English, subject, verb, object is the second most frequently occurring. But there's other ones that are much less represented. So there's some also why, right? You have all these possibilities. Why aren't they like randomly distributed, in equal possibilities? And of course, people have put out all kind of explanations. Well, no, first of all, historically, one sees that there's a tendency for this parameter to shift. There are several examples of transitions from, for example, SOV to SVO, like both ancient Greek and Old English, transitioned. Sanskrit is kind of more interesting because it transitioned at least twice because presumably interaction with the Dravidian languages that belong to a completely different language family and that have parameters set differently. So there are certainly historical effects of interactions between languages that can lead to distribution of these parameters being not equally distributed over the world languages that we observe today. People have also tried all kind of, for example, to put forward possible neuroscience explanations for why certain configurations of syntactic parameters are more likely to be encountered than others, and or internal kind of so. Of course, one of the major possible reasons why parameters might be set a certain way more frequently than another is internal actual relations between different parameters. Like suppose that you have, imagine that these are all variables that can shift and switch, especially in as a fact of interaction between populations. So one thing, how is interaction between languages affecting things like this? So this is something that linguists do study often, is something called code switching. If you have a large population that simultaneously speaks more than one language, it does happen that some kind of syntactic constructions that are possible in one language but not possible in the other languages get adopted into the other language. And so this tends to have, like, if you think of these parameters as having like a 0-1 position, that if this kind of phenomenon happens, they would tend to switch towards a 1 position. This, of course, you would expect if they were all independent variables, you would have, this would be like an Ising model where all the spins align, and you would get, all the parameters switched on. but they're not. I mean, there are relations between different parameters. So, if you have an effect that would tend to flip one of them, it would, it would have to flip a bunch of other things along with that. And some of them might, have an effect that counteracts the switching. So, I mean, one can play with models like this, like you can do one of these, tapo spin glass models, to sort of play with, introducing interactions between the variables. And you see that your equilibrium configurations now become something which is not like all the values up, all the values on. So this is, maybe one of the, ways to think about why, distribution of syntactic parameters is somewhat complicated, across different world languages. Yeah.
Don't linguists talk about ergodicity in the space of parameters and like formal language naturally?
Sorry,
Ergodicity.
in the sense of the dynamics of how parameters switch.
Evolve.
Yes, yeah. So indeed, if you try, like for example, if you try a simple, spin glass model where you flip, you do, one of this kind of Monte Carlo Hastings. I mean, but yeah, then it does satisfy this kind of ergodicity assumption that allow you to say that there is some conversion to some final state, at least in first approximation. I mean, that's not. Of course, the problem is that we don't really have a complete description of this space of parameters, so you have to kind of make some assumptions about what. But let's imagine that you try to imagine a dynamics where basically you have the interaction that says that, okay, if there is a very strong, you can measure it into some proxy for the whatever proxy you want to use for how large is the bilingualism between those two languages, and that would have a term like the model terms where spins would tend to align. But then you have kind of Lagrange multipliers for relations between parameters that would tend to not make them flip if one. And so those, of course, those are like all very rough estimates, but at least, as a kind of qualitative idea of how things would work, then yeah, you would have some kind of convergence to some steady.
Yeah. So there are some languages where word order can be like very flexible, like Russian, for example, where you can like change orders of words to like change the emphasis on a particular word. Whereas like with other languages, like the word order is pretty strict.
Yeah.
Do you know if there's like been much research on that?
That's true. So of course, languages like Russian have a lot of very rich morphology. And so for that reason, you are actually allowed a lot of freedom in changing word order. And so you can change word order for like giving different emphasis to the phrase that you're, so the sentences that you're composing. So this is a reason why indeed, when talking about syntactic parameters, often linguists prefer to talk about morphosyntax rather than syntax separated from morphology. And so you include some of the morphological modification of words into the syntax. And that allows you to take care of these differences. Yes, that's of course an important point to keep in mind. So as I said, there's other examples that are not. So the point is that there are lots of examples where the dependencies between parameters are explicitly known. But there are lots of examples where it's known that there are dependencies between parameters, but they're not explicitly understood. So you can look there are databases where some hundreds of these parameters are classified for several languages. I mean, CETA has done through these databases a lot, but and one can see by looking at the data that there are lots of relations that you can estimate that the actual dimension is much lower than the number of parameters you have, but you don't have like an explicit description of what the relations are. So that's one of the problems of this whole approach of syntactic parameters.
So the slide where you mentioned the neuroscience study, there's many false cognates, false friends across languages that denote some kind of tendency to assign phonetic similarities in two languages that have no diachronic interaction. So is this considered a morphological phenomenon, or is it?
No, so that more happens at the level of lexicon, right? I mean, so for example, if I take the English word much and the Spanish word mucho, is, one would be tempted to say that they have the same root, and they don't. They're completely unrelated. So no, but the lexicon is a very volatile part of language, right? It's very easily changeable. It's very easily, so when you focus on syntax, things are much more stable. As there are examples, and as I mentioned, that show changes in syntax over time, but those are much less frequent than changes in lexicon or in morphology. And in fact, historically, for a long time, historical linguists had based the entire study of how the languages have the like branches of the trees of language families on changes in morphology, primarily, and tracing etymology of lexicon and so on. And it's only recently that been some people who have been doing phylogenetic language trees of language families using syntax, and there on the one hand the syntax is more robust, so it would look like this would be more appropriate. On the other hand, there are lots of instances of situations where you have completely unrelated languages that do happen to have the same syntactic structure for reasons that, might not have anything to do with their historical development. So there's some ways in which syntax is a better type of data to use, and how syntactic parameters change across languages, but there are other ways in which it can introduce this kind of homoplasm that is not significant in historical terms. So. Okay, so so what is meant by government and binding in these all principles and parameters model of language is certain structural relation between the trees of the syntactic parse trees of sentences. So there's two main kind of dependency relations, so to speak, in syntactic trees. One is it's called M commands, where if you have two nodes in the parse tree of a sentence, you say that this node A is M commanding the node B. If neither of them commands the other, in the sense that neither of them is on the path from the root to the other one, but there is like the maximal projection, which I'll say a lot more about later, of one of them is actually on the path from the root to the other one. And there is another form of command relation that was modeled in this setting, which is called C command. And again, is neither of the two is actually on the path from the root to the other one, but the first node that dominates one of them will also dominate the others. So, this is the case here. And these two are both in the C command relation with each other, and this, for example, in the C command relation with these two, but not vice versa. So one of them is slightly stronger than the other condition, and these are like the two main structural dependencies that were modeled in this. And there is another property that is described in this government and binding setting, which is the notion of a barrier between two nodes. Is an intermediate, so it's intermediate in the sense another node that C commands one of them and does not C command the other one. And one says that, a node governs another one, if is in M command with respect to the other one, and there are no barriers between the two nodes. And so nodes here in this setting are labeled. So all the nodes in parse 3 of the sentence are labeled by some kind of lexical category. So something can be like a verb, a noun, an adjective, and once you form a structure, you go to an internal. So this is what you have at the leaves. Some lexical items have a syntactic label of some kind, depending on the role that they play in the sentence. And then as you go to the internal nodes, there's like one it's sort of a substructure has a head, in the sense that there's in a partly formed or fully formed or partly formed sentence, there is like one word that's like the key part, the most important element that would, if you remove it, the whole structure would fall apart. Like, for example, if I have a noun and an adjective, the adjective is modifying the noun, but it could be there or not. But if I remove the noun, then this whole structure falls apart. So that would all be a noun phrase. So I would label the internal vertex to say that if that was a noun phrase, something else would be a verb phrase, in the sense that the head is a verb and the rest is some modifier of that, and so on. So this is like setting the rules for building this kind of parse trees and keeping track of what part is in relation with what part in these trees. And so the binding relation. So this is the government and binding comes from these two type of relations. So I said this is the governing relation, and the binding relation. You're have two nodes, one that commands the other, and they are co-referential in the sense that they refer to the same person or the same actor or whatever. Like, for example, if you have a parse 3 of a sentence like this, John saw his mother, John and his are co-referential because they are the same. They refer to the same. Of course, if you say John saw his mother and his is someone else's mother, then this would not be in the binding relation anymore.
So
Yes.
Is this one to be a co-referential, is that like visible in just from the tree structure itself, or?
Yeah, no, as I said, this requires an additional piece of information, right? The co-referential is an additional piece of information, because I could have this structure, and now there's two possibilities, right? Either the mother, his is John, or his is Tom, right? And you're saying about and so one of them would be co-referential, and the other would not.
But the tree by itself is ambiguous.
Right, so this would have two possible interpretations, and one of them would be in this relation, and the other would not. And of course, if as you expand the structure into a larger structure, then it might resolve the ambiguity one way or the other. Okay, so this is where this general framework that was. So a very, very quick view of some aspects of this general framework of government and binding and principles and parameter. And then, starting with the early 90s, Chomsky introduced what he called the minimalist program, which at the time there's a first book that you had about it that was published I think in 95. It was based on this stuff that was happening in the early 90s. And it was originally formulated as a kind of program, not a complete theory, and in fact, a full mathematical formulation of all of this is still ongoing, which is most of what I will talk about, for the rest of the time. But so it's still formulated within the same idea of principle and parameter setting, though, meaning that there are like some general kind of structure that you want to formulate, which is taking care of the structure formation and basic transformations of structures that are common to all forms of language formation and not specifically language dependent. And then you want a kind of externalization of the structure that takes into account some parameterization that distinguishes different languages. So that idea is kind of remains part of how things are formulated.
So can you define the externalization?
So I will talk about that. So that is in some sense the most delicate part of it, because is basically where you want to model that something like this, like there's some kind of explicitly describable computational process that generates structure that can be treated as sentences and that can be realized as sentences. So there are like you could think of them as being like sentences, some kind of meta language, so to speak, that's that's say prior to realization in one specific language, and then these are realized in one specific language. And of course, when you try, I mean, I'll so spend some time later trying to flesh out the details of this idea, but when you try to understand what that actually means, you see that there are like two kind of operations that this implies. So one of them, for example, is that if the takes into account all this fact that for example, word order is different in different languages, so it means that you have to embed these structures differently in terms of what strings, ordered strings you obtain, and on the other hand, there's certain kind of abstract construction that you can make that are viable in certain languages and not in others, because, for example, they violate some of the syntactic parameters of a specific language and others. So there's also like some kind of some kind of big quotient where a lot of this stuff die out because they're not viable, right? So in a sense, it's this, you can think that this kind of externalization procedure that happens is both an embedding, and the quotient. So in fact, in mathematical terms, one can think of it as some kind of correspondence as you kind of go up and then go down to something that quotients that. But I'll come back to, so try at least to some extent to make that more precise. And so basically the idea of, anyway, what makes minimalism minimalist is the idea that this core computational process that prior to language embodiment into specific language should be in some sense as simple as possible, and should be like modeled on basically one simple operation that could also be justifiable as the evolutionary step that leads to having language available as a computational process. Okay, and so in a sense, like part of what was proposed at the time is that what this should be, what this simple mechanism should be, is something that somehow should be identifiable in terms of some optimality condition, some kind of economy principle, some kind of least action principle, or something that is justifiable in terms of saying that is minimal in an appropriate sense. And I'll not try to again make precise what one can make precise about what this means. So the idea underlying this view of minimalism, and I'll dig into that a lot more in detail later, was at the time that one wants to have two basic operations, one that builds the structure and one that transforms it. Yes.
The screen icon from the corner of the screen, I can see like the top right.
Yeah. Let me try to. Yeah.
Oh, I see.
Yeah, okay.
I thought there was another word there.
All right. So okay. You have you want like two very basic operations. As I said, one that builds the structure and one that tells you how to transform it once it's built. And so at the time in this first formulation of minimalism, these were called merge and move. And like merge would be the one that actually builds the tree, the parse trees of, the structures that are actually, you do think of sentences as being the trees themselves. So that's the operation that constructs them. And move would be the one that's responsible for the type of transformations that we can make on a sentence that's already formed.
Have you shown that here?
Hmm?
Have you shown a move operation on this slide?
Yeah, so I haven't yet, no. So this is basically how you think of the structure formation as kind of, that's like a bottom-up operation that builds structure.
Sorry, could you also remind what the derivation was? What is
Yeah,
derivation?
so that's right. So derivation this is the terminology sort of borrowed from logic. So you just think of it as a sequence of moves in the set. For example, if you are in a formal language, a derivation would be a sequence of applications of your production rules in the given grammar. If you are in a model like this one, a derivation would be a sequence of applications of these merge and move operations that like starts from, for example, you could think of it this way. So I'm building a sentence. So I start from an unstructured set of lexical items with certain syntactic features, and I start to put them together. And so I have various moves in which I partially build pieces of structures and combine them together and make some appropriate transformations so that I can continue building structure. And so the derivation is like the full sequence of moves that takes from this initial set of unstructured items to the final fully formed sentence that you want to have.
So the specific sequence is called the derivation.
That's right. This whole sequence of moves that computes. This is basically your sequence of operations that computes your sentence is called a derivation. So this would be like and so one talks about a derivation in minimalism, or rather than a derivation in like a kind of particular formal language, or to refer to a sequence of applications of whatever moves are available in that system. Okay. So as I said, the merge part is this structure formation that this bottom-up structure formation, and the move part is supposed to take care of the kind of rules that you have in various languages. And so, of course, you see that in this way that I'm describing it now, I'm not making a specific distinction between what is embodied in one particular language and following the rules of one particular language and what is general, right? So for example, let's say, okay, you have certain kind of transformation that you make in English. If you want to form a sentence, you are supposed to change positions to certain items in a sentence, or and to also be able to remember where things have been moved. So even if you don't, like I don't know, if I say he's the cat who is standing on the chair hungry, right? So okay, the cat who is standing on the chair is hungry, and so I'm moving that is on up front when I form a question. But I don't move the first is that I encounter as I'm reading through the sentence, right? This is the cat who is standing on the chair is hungry. If I want to make a question, I'm not taking the first one that I encounter, but I'm taking the first one that is after the noun phrase that contains the first noun phrase, right? So there's the rule of how I'm doing this transformation is seeing the structure, is not seeing just the list, the ordered list of words in the sentence. So that's somehow the idea behind it. You can, of course, other languages, right, will have different rules of how you form a question. So what the example that I'm making is a pretty language specific example. But the point is that you will not encounter any language in the world that, for example, tells you that in order to form a question, you just revert the entire sequence of words, right? Or you change like the fourth word from the left or something like this, right? So there just happen to be no language where the rules of transformation are based on the ordered sequence of words in the phrase. But all the known transformation rules that happen, they are based on identifying certain substructure and moving elements with respect to where they are, with respect to substructures, subtrees of the tree that parses the language. Rules may be different in different specific languages, but they are all of this kind. They're not of other potentially simpler ways of simpler rules that only involve strings.
So while moving parts of the sentence around can be grammatical, you have different connotations. So different examples like passive versus active voice. Is there an interest in keeping track of whether the meaning of the sentence changes slightly, or is semantics out of the question?
Yeah, so no, the interface with semantics, of course, is part of what you want to have at the end. And one of the interesting things is that the way that the syntactic structure is built, of course, affects the way that you can parse the semantics of the sentence. And so there is like this whole way of thinking about the syntax semantic interface, where you try to understand it when you start to assign meanings to sentences. It's again kind of a bottom-up construction where those smaller substructures have their own parsing, but very often you could have ambiguities or things like this, and whether the overall sentence is parsable depends on whether the substructures can fit together in a compatible way or not when you map to semantics. So that's one thing that I plan to talk about later, how one can try to computationally have a way of keeping track of consistency over substructures when you do semantic parsing.
And some cases, like the words you say can be the same, but the intonation can be different, and that can affect the meaning. Is there a way to keep track of that?
Yeah, so that's right. So there are people who have been studied phenomena like this and try to introduce ways to keep into account the fact that in the various languages you can do this. So I don't know. I try to think of some good reference to look at. I mean, it's definitely something that, of course, is noticeable, in various languages. So you want to be able to model that. Of course, all these things is like you have to try to build models. It's like when you build a model for physics, right? You can a priori say, I want to write the laws of motion of something. So I assume that there's no friction, there's no and so on, right? And of course, a lot of these assumptions are not realistic in terms, but of course you try to build this model by introducing more complications a bit at a time, right? Because otherwise, of course, it's like this. These jokes that I mean, you were in my differential equations classes. There's this joke about the mathematician and the physicist who want to bet at the horse races. I said, okay, I want to figure out a way to decide, to find out who's going to win. And so they said they go up way thinking about it and meet again. And the mathematician say, okay, I figured out everything. I know that the solution exists and is unique. And the physicists say, okay, you're totally useless. I tell you, I have a completely explicit solution. It works for all horses with spherical symmetry. So, I mean, obviously we're in a situation like this, right? That, you have a model that works for all languages with spherical symmetry. No, no, it is better than that, but part of the way that you proceed about building these models is that you try to decouple as many things as you can, so that you deal with with one aspect of the problem at a time. And this, is sort of the divide and conquer type of strategy with problems. So you try to break down, modularize like your problem as much as possible, so that each piece in itself becomes something that in itself is rather abstract and maybe not so convincing in terms of capturing all the details that you do have, in actual. But each piece in itself is sort of treatable. And then you kind of try to interface them with each other. So this is like the point of view that one follows with this, which is a reasonable point of view whenever you are trying to model some kind of efficiently complex system. Okay. Yeah.
So do you also keep track of like what is actually like grammatical versus how people speak? Like, for example, like you would say, for whom are you looking? But everyone would say, like colloquially, like in practice, you would say whom. But like, do you keep track of that? And also, who would decide when something is so widely spoken that now it's become grammar?
Yeah, right. So of course, yeah, in a sense, languages don't really exist, right? They are, they are an abstraction. When I say English or French, what do I actually mean? Of course, not only there are huge like regional variation of people speak, there are also differences of how different people speak, and there's there's a continuum. Like if you look at two languages like French and Italian, there's a continuum of dialects where it's completely impossible to decide whether it's a dialect of French or a dialect of Italian, and something like this. So there are all these facts by which, of course, when one talks about a language, this is already an abstraction. And you say something is grammatical in a language if a speaker of that language would recognize it as grammatical. Well, which speaker? Of course, the things do make a difference, and languages are dynamical objects, and so the way that people use them changes over time. So all of these things, of course, are interesting topics of study to linguists, and they are obviously studied quite a lot with linguists. And so, this comes again to the horses with spherical symmetry. You have to kind of make a wide range of abstractions in how you model what a language is and what language is as this kind of phenomenon that embodied itself in different languages. So yeah, of course, this has to be taken into account. So let me switch to that set of slides. Okay. So before I move on to like this other more modern approaches to formulating generative linguistics, I do, because this is a math class after all, so I do want to tell you more about the mathematics of formal languages. So very briefly, since it's not the main focus of this class, but it's a way take the opportunity of doing that as part of this class. So I'll just give an overview of some aspects of the theory of formal languages. Basically, I want to tell you a little bit more about this classification of formal languages into these different classes and the corresponding machine recognition result, the Chomsky hierarchy, which comes out of these old papers. And then I want to just dig a little bit more deeply into these examples that are built using groups, because that's a very good way, in mathematical terms, to capture some of the differences between the different classes of formal languages. So let's go back to the formulation of general formulation of the setting of formal languages. You have some finite set, which is your alphabet, and is considered, well, you can use letters or any kind of symbol that would correspond to like your lexical items in an actual language, but you can just think of them as zeros and ones, this is two, or a number of symbols.
Does this include punctuation?
Hmm?
This includes punctuation?
This would include punctuation if you were to model a language. It would include like space, the space symbol to separate words, so whatever. And or I mean, you could decide to forget about punctuation. I mean, you could, yeah, depending on whether you want to have that as part of the structure or not. It would just be words or not. And so words are just any string in this alphabet, and you do consider usually you consider also the existence of a possible empty word for which is just convenient sometimes for calculation, and you have so you can have the set of words of arbitrary length, or either including or excluding the empty word. And this is either a semi-group or a monoid under the simple operation of concatenation. So you have like a text is an arbitrary string of words, and you have concatenation of text in this form, which is an associative operation. And you can, well, a subword is just some substring of the string, and that determines also what the prefix and the suffix is once you have a subword. And so in this sense, a language is just some subset of this set of all the possible strings in your given alphabet. And the question from the formal language viewpoint is, how is such a subset constructed? So in general, the way that one thinks about constructing subsets of this set of all possible words in a given alphabet is through a rewriting system. So this is a relation in the set of all possible strings in your alphabet. So it's a subset of the Cartesian product of this set of strings with itself. And if you have an element in this relation, it means that this string can be rewritten, replaced by the other one. And so if you encounter that string in the middle as a subword of some text, you can replace it with the other one and keeping the rest of the text the same. And so one writes this notation for one of these operations. And then, yeah, in this sense, a derivation in this sense is a sequence of such strings, or if you want a sequence of such rewriting operations, one after the other, that goes from beginning to end of this story.
So this is providing some kind of morphism between languages.
Yeah, so you could. So in this sense, I'm kind of still saying like what a language is, right? In the sense that I'm telling you how to construct a certain subset. Then of course you could say once you have these, right? Each one of these then would itself be a monoid under composition, and you could then have like morphism between things, for example, by relating this rewriting operations.
So then could you say that language is just a subcategory of set?
You could, yes. I mean, you can view it way. You can view it as themselves as submonoids of this of a given monoid. I mean, yeah, there are some more category oriented ways of formulating generative grammars also, which can also be proved to be equivalent to some of this formalism that I'm describing, those categorical grammars. Yeah, I mean, at this level, one could just define this way, but describing the transformations, rewriting rules. And just this is going back to what I've already shown, that then one can describe a grammar as something that has known terminal and terminal symbols, and some of these rewriting rules, a finite collection of rewriting rules. and you can, then the language is, all the strings in the alphabet of the terminal symbols that are obtained as a derivation that repeatedly applies some of the rules that you have available in the set of production rules, starting with some assigned start symbol. And so coming back to this classification of different types that I mentioned before, the most restrictive one is the regular grammars, and one can explicitly define them in this way. So remember that I've already given you like the punchline about the regular grammars, which they are paths on some directed graph. So you can always like write the production rules as telling you what the next step in the path is, and so you just get some collection of labels assigned to the directed edges of your graph. And so that's why you can always write them like this, or the other way, depending on how you write composition, right, in one order or the other. But so I mean, one can take this as being the definition of the regular grammars. The context-free and the context-sensitive grammar I've already discussed last time, what way that the rules look like, and the unrestricted grammar of type 0. I'll come back to say more carefully what it is, but basically it's related just to computability. It's the most where you don't put any restriction on how the actual production rules look like, but you just make a computability assumption that I'll be more precise about in a moment. But so I've given some examples already, right, of things that are context-free but not regular, and context-sensitive but not context-free, depending on the different type of recursion that you can have. It's a bit more difficult to construct an example that is of this more general computable class, but not context-sensitive. And the way you can do it is by one of these tricks, like Gödel numbering, that works like this. You kind of construct a certain family of grammars, that are built, by a set of strings that you can encode in binary strings, and then you define your language as being the words that are of a certain type in terms of sequences of zeros and ones. So in each of this language, you have certain kind of sequences of zeros and ones, and you kind of repeat them an arbitrary number of times. And now you look at all the possible sequences of zeros and ones in this form, but they are not in any of these ones. And you can show this an argument that shows that if these were context sensitive, you would be able to reduce it to something that can be encoded in this way, and so it cannot be context sensitive. So it's a kind of slightly more argument, but I'll come to examples that again, when one looks at the class of examples like the ones that are coming from groups, it's easier to see like where examples like this are coming from. And one can gather by pretty explicit ones where I'll show in a moment. So, as I mentioned already, this distinction in types corresponds to a different type of automata that can compute this language. So maybe just a little more precise on the definitions. I've already kind of shown the pictures, so it's just a matter of formalizing those. So when you say that something is a finite state automaton, you have a finite set of possible states of the machine. Of course, these are going to be the vertices of your directed graph. And one of them is marked, one or more of them are marked as being the final state or final states. And you have well, it would be like sinks, right, of your directed graph, and you assume that you have one initial state, and then you have a finite set that is an alphabet that marks the edges, the directed edges in this graph. So the set of possible transitions of the finite set automaton is a subset of the product. So it tells you the source and target vertices of your arrow, and it tells you what label you put on the arrow. So that's And so a computation in a finite state automaton is a sequence of going around the edges of your directed graph. So you can view it as a sequence of vertices that you transverse in this path, and the corresponding labels that you read on the edges that you're taking to go along this path. And so this computation is labeled by the string of labels that you read on the edges. And so you say that the finite state automaton accepts a certain string if there is a computation of that sort that correspond to this string. So it's like I give an instruction. So this is like the instruction that I read on my tape. And if my machine can follow a path on the graph that corresponds to that sequence of instructions, and that sequence of instruction is realizable by the machine. And so so if all the words in a given language correspond to strings that can be computed, then that language is computed by the finite state automaton, or recognized by the finite state automaton.
Question?
Yeah.
So you said earlier that the formal language approach is deficient because it reduces everything to a sequence of strings. But a sequence of string can lend itself to all kinds of algebraic structure if you add some kind of decorations and operations. So is the problem that trying to translate it into this machine computable is not easy?
That's right. Yeah, that's part of the problem, right? Around using this formal language viewpoint. So this is very good for describing the strings of whatever, or words, whatever it is, with some properties. Like, for example, it is very good for this type of examples that I gave, like distinguishing between certain kind of recursions of different types. And so those are properties of strings of words. And it becomes more difficult to formalize in this context various kinds of transformations on strings that have to do not with, so you can in a sense more easily formulate transformation of strings that really have to do with the strings themselves. But as I was saying, a lot of the transformations that we do use in languages are not things that are easily describable in terms of the string itself. They are usually described in terms of trees that have the string as their leaves, and these are not at least at the level of formal languages described in this form, not easy to implement. There are classes of formal languages. I'm going to say a few words about, for example, the tree adjoining grammars. Those are kind of designed to be formal languages that use the tree structure already as part of the language. One can also, for example, for the context free case, associate to a chain of derivation in the sense on the context free language. One can associate a tree, and so one can try to build more structure in that way. But again, the problem is that it becomes quite complicated to introduce this other type of transformation in this formalism. So in fact, this first step after the theory of formal languages was developed, that was this transformational grammar point of view, was based exactly on this idea. So you kind of have a formal language, that is a context-free grammar that takes care of the formation of trees, and then on top of that you describe some transformations. And so it was exactly trying to do it this way, which is kind of a natural thing to do. Is say, okay, I can produce the strings, but now I can also keep track of the structure as the steps that I've done in the calculation, in the actual derivation that gives me the string, and then I try to make transformation of those. And so this whole period, like in the 70s, when people studied transformational grammar, was pretty much used on doing this combination, some context-free formal language for structure formation, and then transformations of that. But again, it's sort of like more complicated than one expects that it should be, to do it that way. So that was one of the reasons why then things kind of transformed into something more that more or less did not follow anymore like this informal language perspective. Okay, so yeah, I mean, as I said, this has walks in graphs, kind of paths in graphs description. And yeah, there's a distinction in informal languages. You often find this distinction between deterministic and non-deterministic formal languages. So it simply means the following thing, right? That if I have a transformation, which something that says I'm at state Q, I read A on an arrow and I end up at state Q prime. So my automata, automata is deterministic. If I have these two data, there's a unique Q prime that is determined by these two. So that this is actually enough to specify my transformation. I know where I am and I know which label I read on my instruction tape, and then I know where I'm going to be. Or it's non-deterministic if you have more than one such choice. So if you have like more than one arrow in your graph, two different other vertices, but with the same label. And which means that you have multiple ways of realizing the same word in your automaton and not necessarily a single unique one. So the languages that are recognized by a finite state automaton, no matter if you want it to just be deterministic or you allow also for the non-deterministic one, are of these type 3 form. And I kind of already told you why, in the sense that if you have a type 3 grammar, you much can use the production rules that not always going to be of this form, or map into a terminal to either be an arrow. So if you take the vertices of your graph to be given by these non-terminal symbols and the final state. And then, whenever you have a production rule that involves two non-terminals and terminal, you have a narrow label by that terminal, and if you have something that just ends at the terminal, you just have an arrow that takes you to the final state. And then this is the final state automaton that realizes it. And conversely, of course, if you have a final state automaton, you just read off the arrows and you use the arrows as your production rules. And you get a type 3. So the push down stack automata are a way to introduce the possibility of having some amount of memory storage that allows, for example, for the type of recursion where you have to memorize something in order to coordinate these two recursions. And the push down stack is a type of memory where you have a string that can be deposited, a string in a certain alphabet that can be deposited in the stack, but you can only always access the last thing that the last thing that you put in in. So the idea is very similar to how you describe one of these push down stack automata, but I think I will have to tell you about it next time. But basically, sort of the same. You have a directed graph, but now instead of just having the labels that you put on the edges, you also have another alphabet that is what you can deposit in the stack and what you can read at the top of the stack. So your instruction read your labels of the edges, but also read what you have at the top of the stack when you decide where you're going with the next move. Okay, so next time I'm gonna just finish this formal languages stuff, and I will tell you a little bit more about the merge, these early versions of minimalism, especially in the kind of more computational form. So there's a kind of a computational minimalism that's also the way that people try to realize this in terms of explicit writing programs for explicit derivations. And then I think with that I'll have like covered all the background that I wanted to cover before starting talking about the new stuff. Okay.